Properties of scalar multiplication. Hello everyone. To begin, let's quickly recap what we have already covered. In our previous sections, we learned that scalar multiplication is the process of multiplying every single element within a matrix by a constant real number, which we refer to as a scalar. Now that we understand the basic mechanism of how to perform this operation, we will move into this subsection to explore the algebraic properties associated with it. Specifically, we are going to examine how scalar multiplication interacts with other operations, namely, the addition of two matrices and the addition of two different scalars. Understanding these properties is essential because they provide us with the necessary tools to simplify complex matrix expressions, allowing us to manipulate them with the same logic and efficiency that we use in basic algebra. Distributive law over matrix addition. Now that we have established the basics of scalar multiplication, let's dive into the specific algebraic properties that govern this operation. Our first focus is the distributive law over matrix addition. To state this formally, if we have two matrices, A and B, which are of the same order, and a scalar k, then k times the quantity A plus B is equal to k times a plus k times B. In simpler terms, this property tells us that there are two different paths to the same result. If we first find the sum of two matrices and then multiply that total by a scalar, the outcome will be exactly the same as if we had multiplied each matrix by the scalar individually first, and then added the resulting matrices together. To see how this works in practice with actual numbers, let's move on to the next slide for a step-by-step example. Step-by-step example for distributive law over matrix addition. Now that we have discussed the formal statement of the distributive law over matrix addition, let us apply it to a concrete example to see how it works in practice. For this example, let us take the scalar k to be 3. We will use two 2x2 matrices. A and B matrix A consists of 1 and 2 in the first row and 0 and 4 in the second row. Matrix B consists of 5 and -1 in the first row and 2 and 3 in the second row. Let us first explore method 1, where we calculate k times the quantity A plus B. In the first step, we find the sum of A and B by adding their corresponding elements. 1 plus 5 gives us 6, 2 plus -1 gives us 1, 0 plus 2 gives us 2, and 4 plus 3 gives us 7. This results in a matrix with 6 and 1 in the top row, and 2 and 7 in the bottom and bottom row. In the second step, we multiply this resulting matrix by our scalar, 3. By multiplying every single element by 3, we arrive at a final matrix containing 18, 3, 6, and 21. Now, let us see if we get the same result using method 2, which is calculating k times a plus k times b. First, we find k times a multiplying every element of matrix A by 3. We get 3, 6, 0, and 12. Next, we find k times b multiplying every element of matrix B by 3. We get 15, -3, 6, and 9. Finally, we add these two resulting matrices together. 3 plus 15 is 18, 6 plus -3 is 3, 0 plus 6 is 6, and 12 plus 9 is 21. As you can see, both methods yield the exact same final matrix. This confirms our property. K times the quantity A plus B is indeed equal to k times a plus k times b. Having mastered how a scalar distributes over matrix addition, we will now move forward to look at how a matrix distributes over the addition of two scalars. Distributive law over scalar addition. Now that we have explored how a scalar distributes over the addition of two matrices, let's move on to the second property. This property focuses on the distributive law over the addition of two scalars. To state this formally, if we have a matrix A and two scalar constants, k and L, then the sum of k plus L, multiplied by matrix A, is equal to k times matrix A plus L times matrix A. In simpler terms, this property indicates that multiplying a matrix by the sum of two scalars is equivalent to multiplying the matrix by each scalar separately, and then adding those two resulting matrices together. To see exactly how this works in practice, let's move to the next slide, where we will walk through a step-by-step numerical example. Step-by-step example for distributive law over scalar addition. To begin, let us define our variables. We will use two scalars, k equals 2 and l equals 5. For our matrix A, we will use a 2x2 matrix, where the first row consists of 4 and -2, and the second row consists of 1 and 3. We will now explore this using two different methods to verify the property. First, let us look at method 1, where we calculate the sum of the scalars first, and then multiply that result by the matrix. In step 1, we find the sum of our scalars, 2 plus 5, which equals 7. In step 2, we multiply matrix A by this resulting scalar, 7. By multiplying every single element within the matrix by 7, we arrive at a final matrix containing 28 and -14 in the first row, and 7 and 21 in the second row. Now, let us see if we achieve the same result using method 2, where we multiply the matrix by each scalar individually before adding them together. In step 1, we calculate 2 times matrix A, which gives us 8 and -4 in the first row, and 2 and 6 in the second row. In step 2, we calculate 5 times matrix A, which results in 20 and -10 in the first row, and 5 and 15 in the second row. Finally, in step 3, we add these two resulting matrices together. By adding the corresponding elements, 8 plus 20, -4 plus -10, 2 plus 5, and 6 plus 15, we get a matrix with 28 and -14 in the first row, and 7 and 21 in the second row. In conclusion, since both methods yield the exact same result, we have numerically proven that the sum of scalars k plus l, multiplied by matrix A, is equal to k times a plus l times A. Now that we have discussed the theoretical framework of the distributive law over scalar addition in the previous slide, let us apply this concept to a concrete example to see how it works in practice. This mathematical consistency is very useful, and in the next slide, I will share a real-world analogy to help you visualize why this property makes sense in a practical scenario. Real-world analogy. Imagine a company that operates two different warehouses, which we can represent as matrix A and matrix B in this scenario. The elements within these matrices represent the quantities of two different products stored in each location. First, let us apply the first property we discussed, the distributive law over matrix addition. Suppose the company decides to triple the stock in both warehouses. They have two ways to approach this. They could first add the current stock of both warehouses together to find the total and then triple that sum. Alternatively, they could triple the stock in each warehouse individually and then combine the results. As we saw in our previous example, the final inventory will be exactly the same regardless of the method used. Next, let us look at the second property, the distributive law over scalar addition. Imagine a manager decides to increase the stock of a single warehouse by 2 times in the morning and then by another 5 times in the evening. This is logically the same as simply increasing the stock by 7 times in one single operation. Now that we have walked through the formal mathematical proofs and examples, let us put these properties into a real-world context to make them more intuitive. By visualizing these properties through this analogy, you can see how matrix algebra mirrors real-life logic and basic arithmetic. However, while the concepts are straightforward, there are some technical pitfalls to be aware of. In the next slide, we will discuss the common mistakes to avoid when performing these calculations. Common mistakes to avoid. First, let's address partial multiplication. A frequent mistake students make is multiplying only the first row or the first column of a matrix by the scalar. Please remember that, as we established at the beginning of this lesson, scalar multiplication must be applied to every single element within the matrix without exception. Secondly, be careful not to confuse scalar addition with matrix multiplication. Specifically, do not confuse the expression, k plus l, all multiplied by matrix A, with K multiplied by the quantity L times matrix A. While both operations are mathematically valid, they represent different properties. The first is the distributive law over scalar addition, which we just examined in our previous examples, while the second is known as the associative law of scalar multiplication. Finally, let's talk about order mismatch. When you are applying the property K multiplied by the sum of matrix A and matrix B, you must first ensure that matrices A and B are of the same order. As we discussed in the earlier sections on matrix addition, if the dimensions of the two matrices do not match, the addition of A and B is undefined, and therefore, this property cannot be applied. Now that we have explored the distributive properties and seen them in action through examples and analogies, it is crucial to discuss some common pitfalls to ensure you avoid these errors in your calculations. Keeping these 3 points in mind will help you maintain accuracy in your work. Now, let us move to the final slide to summarize our key takeaways. Key takeaways. First, let's revisit the distributive law over matrix addition. As we demonstrated in our earlier example, K times the quantity A plus B is equal to K A plus KB essentially. This means the scalar K distributes to each individual matrix within the parentheses. Next, we have the distributive law over scalar addition. This is the property where the quantity K plus L, all multiplied by matrix A, equals K A plus LA in this case. The matrix A is what distributes across the two scalars. Ultimately, these properties are vital because they ensure that matrix algebra remains consistent with the distributive laws you are already familiar with from basic real number arithmetic. This allows us to simplify complex matrix expressions using the same logical foundations we use in standard algebra. Alright, let's wrap up everything we have discussed in this section by reviewing the key takeaways.